So now we can add them all together and find the total solution. And the total solution then is going to be C1 e to the minus t plus C2 e to the minus 4t plus 24. And now and only now can we substitute in those initial conditions. So let's do that. Who's up next? Philip. Let's substitute the initial condition for v sub c at 0 plus. What is it?
Right, you're going to get C1 plus C2 plus 24.
Yeah, C1 plus C2 plus 24. So we're just substituting in 0 in here. And what does that have to equal?
That's going to be equal, I guess, what, to 0. No, to the initial condition. Sorry, I need to look back. Is that what, 2 volts?
Yep, that's 2 volts from all the way over in our lower left. So therefore, we can rewrite with our constants on our left and with our unknowns on our left and our constants on our right. That gives us
negative 22.
Negative 22. Thank you. Okay, how about our v sub c prime at 0 plus? From our initial conditions, Philip, I'm going to stay with you for here. It's going to be 8 volts per second. But take a look at this equation, take its derivative, and set it equal to 0, and what do you get?
Negative C1.
Yep.
Minus 4 C2.
That's it. And then what happens to the 24?
It turns to 0 because that's what happens to the derivative.
That's it. And so now putting again the unknowns on one side and the constants on the other, we get this. Now we've got 2 equations and 2 unknowns. And you can solve them using any method you want. Your calculator, I think for this thing, it's just begging for us just to add up the values, which cancels out our C1. So it'd give us minus 3 C2 equals minus 16, is it? 14, minus 14. Yeah, that's right. So therefore, C2 is equal to 14 over 3, which is 4 2/3. And now we could substitute that back into our first equation and say C1 has to be equal to minus 22 minus C2, which is minus 22 minus 14 over 3, which is minus 26.67. And so now we can write the entire problem. It's equal to minus 26.7 e to the minus t plus 4.67 e to the minus 4t plus 24. All that units is in volts. And what if instead of asking to find what VC is, I asked to find it for all time? So what region is this correct for? Sabine?
Is this correct for time greater than 0?
That's it. So what would it be for time, just continuing with you, Sabine, what would it be for time less than 0?
It would be, wouldn't it just be 24 or?
That's what it would be at infinity. And that's what we figured out up in the upper right, at time equals infinity.
So would you plug in 0 and then solve using your e to the 0 and so
nope.
it'd be?
Because all this work for the natural and the force, that's only true for time greater than 0.
So would it just be 0 then?
No, you'd have to go back and redraw it for time less than 0 to find out what it would do for time less than 0. But it would be in DC steady state, right?
Yeah, so, and we found that to be 2 volts.
Bingo, you already did it, and you found it to be 2 volts. So now you've got the whole solution for all time. That's it exactly. And that's it.
So, sir, I have a question about reporting this answer.
Sure.
Do you want it in the form that you have here, or do you want us to use like unit step function?
Up to you. I would probably I mean, if I don't specify, do it whatever is simplest, which is probably the way that I just did it.
Thank you, sir.
It would be, you could do it using unit step functions, but it would be challenging to do. It would require a lot of mucking around with some nasty looking stuff. Let's see, how hard would it be?
Wouldn't it just be the 24? Like you just add 22 plus the rest of the equation?
So you could say it's equal to
this example.
minus 22 plus all of that stuff plus 22 u of t. Yeah. That would work fine too. Yep, that would work fine too. Thinking about what else I want to talk. Firstly, do you guys have any questions about this problem?
I have a question regarding the calculus done when we took the derivative. How exactly did it go from e to the negative t after you take the derivative to negative c1 and minus 4?
Yeah. So let me write this in a different color to make it clear. Your question is how do we get that so fast? And the answer is that, just doing it down here, we said that the true derivative of this whole function is equal to minus c1 e to the minus t minus 4 c2 e to the minus 4t. So I'm just taking the derivative of this over here. So is that a thumbs up? And then we evaluate that at t equals 0. And at t equals 0, we get minus c1 minus 4c2. And we set it equal to what our initial conditions were over here, which is equal to 8. And that's how we get our equation. So I just want to review everything before we get off. First step is we want to find initial conditions. And to find those initial conditions, we firstly draw it for time less than 0. We have no switches. We have no U of T's. We convert capacitors to opens and inductors to shorts. And no matter what you're asked to find, we're going to find I sub L and V sub C. In our second step, that's when we're going to find whatever we're asked to find and its derivative. We also have no U of T's and no switches. This time, though, the capacitors become voltage sources and the inductors become current sources. Our next step is we want to find our natural solution. To do that, we draw it for time greater than 0, and we find our alpha. And there's 2 different possible values of alpha, depending upon whether or not we have our circuit in series or in parallel. We always use the same equation for omega naught. We always use our same equation for S. We next look to see which of these 3 solutions for alpha will we use. And depending upon which relationship of those 3 possibilities with alpha, we'll use one of these 3 possibilities for our natural solution. We then find our natural solution, and it's going to have, which we just read out from up here, plugging in our S values, and it's going to have unknowns. And we want to keep those unknowns there. We do not want to solve for our unknowns. Our third step is we want to find the forcing solution, the particular solution, the language of differential equations. We call it the forcing function, though, because it's the forced solution for whatever our forcing value is in our circuit. Then you add the forced solution to the natural solution, and at that point you substitute in the initial conditions. And no matter which of these 4 types of natural solutions you've got, it's going to end up with 2 equations, 2 unknowns. Solve it however you want to, and then you're done. And that's different than in the first order equation, which is then you have to ask, what the heck are you asked to find? Here, you've already found it. You've solved for whatever you're going to ask to find. If there are no questions, I'll let you go, and I'll see you on Monday.